Welcome back to the final session of the MOOC on Information Security. Today's topic is System Call Monitoring. System call monitoring is a technique for detecting and controlling compromised applications by checking at runtime that each system call conforms to a policy that specifies the program's normal behavior. Computer systems have long been subjected to attacks that involve either altering existing code to take malicious actions or introducing new executables into the system that later compromise the system in some way. Worms, for example, propagate by altering program executables on their target. The executable might be a running program that the worm corrupts through a buffer overflow, an executable overwritten by a microprogram contained in an email message, or a library installed from a corrupted code repository as part of a regular software update. This wide mix of both targets and techniques make it challenging to develop countermeasures, especially those with broad applicability. Despite the different approaches used to introduce altered code onto a machine, these attacks share one characteristic. They typically exploit the system call interface to take malicious action. It is only through this interface that compromised code can, for example, write to the disk or send a network packet. System call monitoring is a widely used technique that exploits this characteristic to detect compromised applications and sandbox them to minimize the damage they can cause. A simplified version of a system call monitoring is illustrated in the figure. The System Call Monitor or SCM checks system calls at runtime using the application's policy and either allows or disallows them depending on whether or not they match the policy. In the figure, the vertical line from the application through the SCM to the OS kernel on the left labeled A illustrates a call that is allowed to proceed after being checked by the SCM. The line on the right labeled B, on the other hand, illustrates a call that is blocked by the SCM because it does not match the policy, that is, deviates from the application's normal behavior. Issues that must be addressed to realize such an approach include implementing the SCM to minimize runtime checking overhead and vulnerability to attack determining an application's normal behavior and using that to generate policy, and making policies available to the SCM at runtime. General principles. The biological analogy led to a set of general design principles which remain relevant to computer security more than a decade later. These include generic mechanism. A generic mechanism that provides coverage of a broad range of attacks even if it is not 100% probably secure for any particular threat model. This approach is similar in spirit to universal weak methods in artificial intelligence that are applicable to many problems and do not require specialized domain knowledge. Although some of the pattern recognition mechanisms of the adaptive and innate immune systems are biased towards detecting important classes of infection, many are generic danger detectors. The existence of autoimmune disease provides evidence that they are imperfect, yet they are highly effective at eliminating infections, and natural selection has conserved and enhanced immune systems in all higher animals. Likewise, choosing a universal and fundamental data stream such as system call allowed us to design a system that could protect a wide variety of programs against a wide variety of threats without specialized knowledge. The second one is adaptability. This means adaptable to changes in the protected system. Computer systems, environments, and users are highly dynamic, and normal legitimate users of the systems are continually evolving. Just as biological defense systems need to cope with natural adaptive processes, so must computer security systems if they are to be robust. In our system, adaptability was achieved through the use of simple learning mechanisms which were used to construct models of normal behavior and to update them over time. Autonomy. Computer systems have traditionally been thought of as tools that depend upon humans for guidance. However, as computer systems have become powerful, numerous and interconnected, it is no longer feasible for humans to manage them directly. Biological systems necessarily operate independently, online and in real time because they live and interact with physical environments. In our system, we addressed this requirement with the most lightweight, simple design we could think of, ignoring system call arguments, modeling data with simple data structures, and without calculating probabilities or frequencies, and a generic response mechanism that slows down suspicious processes. Graduated response. In computer security, responses tend to be binary. As in the case of access controls, either a user is allowed access or not. Firewalls, either a connection is blocked or it is not. Or cryptography, where either a file is encrypted or it is not. Biological systems have graduated responses, where small perturbations result in small responses and large deviations cause more aggressive responses. We adopted this principle in process homeostasis, where system calls were delayed according to how many anomalous system calls had preceded them. Graduated responses allowed us to move away from the concept of security as a binary property and to tolerate imperfect detection. The fifth one is diversity of the protection system. Natural immune systems are diverse. Individual differences arise both through genetic variations, example MHC genes, or through life histories, example which immune memories an individual has. Individual diversity promotes robustness because an attack that escapes detection in one host is likely to be detected in another. Assuming that hosts have finite resources to devote to defenses, this allows a higher level of population level robustness than could be achieved by simply replicating the same defense system across systems. Beyond that, diversity of the protection system makes it much more difficult for an attacker to design a generic attack that will succeed everywhere. In our system, different environments and usage patterns confer diversity on each program invocation, which leads to diverse patterns of system calls observed during normal behavior. Policy issues. Many different system call monitors have been developed that vary in how they address the following fundamental issues related to policies. First one is policy expressiveness. What policies can be enforced? Another one is policy creation. How is the policy of an application is determined? Policy enforcement. Are policies enforced in the kernel, outside the kernel, or using some combination of the two approaches? Policy expressiveness. In system call monitoring, each system call in a program has an associated system call policy that specifies properties that must be satisfied when the call is executed. The program's overall policy is the collection of its system call policies. In principle, a system call monitor should be able to enforce any computable policy. In practice, however, most system call monitors restrict the class of policies that they enforce for reasons of either efficiency or simplicity. The properties expressed by a system call policy can be viewed as constraints on the execution of the system call. A typical policy, for example, may require that a system call be constrained to a specific system call number or name, or must be invoked from a particular memory address in the program called call site, or both. It might also specify allowed values for the arguments using either concrete values, for example 5, or some path like /dev/console, or patterns, for example /tmb/star. Policies of these types are used in many existing system call monitoring systems. System call policies can also constrain more global behaviors, such as the acceptable order of system call executions. For example, the collection of system call policies for a program might constrain the application's system call trace to be a path in the call graph. In this case, each system call policy could include a list of system calls that are possible predecessors for the given call. While system call policies can be quite general, they do not have one inherent limitation. They can only be checked when a system call is invoked. As a result, system call monitoring cannot prevent attacks such as buffer overflow. Once a monitor approves a system call that reads into a buffer, there is no mechanism in place to prevent the read from going past at the end of the buffer. Rather, the goal of system call monitoring is to isolate or sandbox compromised applications to minimize the damage they can cause. Therefore, in system call monitoring, a process can become corrupted through a buffer overflow or some other attack and then run freely as long as it does not make a system call. Depending on the operating system, such a process can consume significant resources or take other actions that affect the system. For example, under Linux, a process can consume CPU cycles, access its memory space to cause paging, or even perform reads and writes to files that were memory mapped before the attack occurred. However, the process would not be able to open new files or even write to files or network sockets using file descriptors, since those operations involve system calls. Policy creation. System call policies are meant to capture the normal legitimate behavior of a program. In practice, three techniques can be used to create policies, such as manual, training, and static analysis. Manual. Policies can be written by hand. In training technique, policies can be learned by examining some sample runs of the program. In the static analysis method, policies can be determined through static analysis of the program. Handwritten policies can be extremely valuable, particularly when they are written by someone with deep knowledge of the program. However, they are tedious to produce and maintain, so they are most often used selectively in combination with the other two techniques. Most existing system call monitors determine policies through training. Training can be automatic, so policies are easy to produce and maintain. However, training by its nature does not examine all possible behaviors of the program, so policies produced through training may be overly restrictive. This is a significant barrier to the use of the system call monitor, because system administrators must either spend a lot of time checking false alarms or start ignoring alarms, including alarms for real attacks. Policy enforcement. A system call monitor checks each system call against its policy at runtime and either accepts or rejects the call. This security critical check can be performed in user space or in the kernel. Systems that intercept system calls in user space can be vulnerable to corruption by such exploits as buffer overflows when applied to programs written in unsafe languages. Such an approach may, however, be appropriate for programs written in safe languages such as Java, or in systems where unsafe languages are compiled with additional checking for safety. Implementation of authenticated calls using system call. An authenticated system call is a system call augmented with extra arguments that specify the policy for that call and a cryptographic message authentication code or MAC that guarantees the integrity of the policy and the system call arguments. This extra information is used by the kernel to verify the system call. The version of the application in which regular system calls have been replaced by authenticated calls is generated automatically by an installer program that reads the application binary, uses static analysis to generate policies, and then rewrites the binary with the authenticated calls. Now let's summarize. An authenticated system call is a system call with additional arguments that specify a policy that the system call should satisfy and a message authentication code or MAC that guarantees the integrity of the policy and other arguments to the system call. The policy and MAC are part of the untrusted application, but the MAC is computed with a cryptographic key that is available only to the kernel. At each invocation of an authenticated system call, the kernel uses the key to recompute the MAC and only allows the call to proceed if this matches the MAC passed by the application. Hope you enjoyed this session. I hope this MOOC on information security was fruitful for you in your life to use your devices and information in a secure manner. Thanks for watching. Bye.